Alright guys, so today we're going to be covering the Hardy-Weinberg equilibrium, and we're going to be doing the math portion. So in our notes yesterday we just kind of introduced the Hardy-Weinberg concept, and the whole idea behind it is that a population can be in equilibrium if those 5 conditions are met. And so in equilibrium, that means allele frequencies aren't changing. And so in order to have that, in order for no change to occur, you would have to have completely random mating, no mutations, no natural selection. You'd have to have a really large population with no genetic drift or random changes. And then you'd also have to have no gene flow. And so the reality is those can't be met in a natural population. And so for the math portion of Hardy-Weinberg, it's a way to calculate allele frequencies in a population. And so you could calculate those frequencies, wait a few generations, calculate them again, and then it could show if the population was changing. And so you have 2 different equations, and you should have a paper that looks like this. Okay, so it kind of gives you the background information. It's got those 5 conditions that are impossible to meet. And then it kind of goes over these 2 equations. Now, I do want to clarify and that you could only use these equations for a single gene trait that has 2 alleles. Okay, so what we have is not that spectrum. We don't have that range of phenotypes. We essentially have a dominant allele, a recessive allele, and we're going to have a dominant trait and a recessive trait. So we can only use these equations for those types of inheritance patterns. But it's a mathematical way to calculate allele frequencies in a population. And so here I have the 2 equations written down. Okay, we've got P plus Q equals 1, and then we've got P squared plus 2PQ plus Q squared equals 1. And so we're going to take a look at each of these equations. And first of all, you have to know what they represent. The math is not difficult, but we do need to understand what variable we are solving for and how we represent those variables. So I'm actually going to start with this equation here, P plus Q equals 1, and these represent my allele frequencies. Okay, now I do want you to notice that they're equal to 1, so when it asks for a frequency, your answer should be in decimal form. Okay, and in general, unless you have to carry it further, I would typically round off to the hundredths place. Okay, that's just your general rule of thumb. But notice, because they equal 1, when it asks for a frequency, it's expected that your answer is going to be in a decimal form. Now, if they specifically give you a percent, you would convert it to a decimal, or if they ask you for a percent, you would then convert your decimal to a percent. And hopefully you guys know how to do that, moving the decimal forward or backward. So when we say allele frequencies, that means that these letters represent the alleles in that population. So P represents the dominant allele, or capital A, and Q represents the recessive allele, or lowercase a. Once again, we can only do these for single gene traits with 2 possible alleles, dominant, recessive. Now, the other equation is going to represent genotypes. It's going to be a genotypic frequency. It's also going to be your phenotypic. Because remember that your genotype determines your phenotype. The genotype are your letter combinations, and the phenotype is what you see. So if P is big A, then P squared represents a homozygous dominant genotype, okay? And then if Q is little a, then Q squared is going to represent a homozygous recessive genotype. And then here I have 2PQ. Well, P and Q would be big A, little a. So 2PQ represents your heterozygotes in your population. And so for this one, the reason you get 2 is technically you could have PQ or QP, and so there's 2 possible combinations there. But these are the 2 equations that we're going to use. And from these 2 equations, we should be able to solve any question about allele frequencies, genotypic frequencies, or phenotypic frequencies, okay? Now, the only thing we haven't labeled are the phenotypic. And so just going back to genetics, remember that the only way that you can see the recessive trait is if you have 2 lowercase letters. So your recessive phenotype is also going to be represented by Q squared. And then when it comes to your dominant phenotype, remember that capital A would demonstrate the dominant trait, and capital A lowercase a would also represent the dominant trait. So for phenotypic purposes, both of these will have the dominant phenotype, okay? So when we're doing the Hardy-Weinberg problems, they pretty much always have the same flow, and I'll explain to you why we always pretty much start in the same place. So if I'm looking at a natural population, okay, I could be looking at butterflies, I could be looking at humans, I could be looking at raccoons, I could be looking at anything. But if I'm looking at one of these genetic traits, I cannot physically look at an individual and see what letters they have, okay? I can't count how many dominant alleles there are. I can't count how many recessive alleles. All I can see when I physically look at a population is I can see phenotype, okay? So I don't know the genetics of the population, but I do know what traits they have, what they look like. So when it comes to looking at a population, the only thing that I know out of these two equations, the only thing that I can determine is Q squared, okay? Because if I look at a population, let's say we're counting freckles in the classroom. If you have freckles, you're dominant. But if you have freckles, do I know if you're big A or big A little a? I can't see that. But I do know that if you don't have freckles, I know what your genotype is, okay? So we gotta use these equations together. They go hand in hand. And they're pretty much every problem that you do is going to have the same flow, okay? And just, I want you to understand that our starting point for pretty much any Hardy-Weinberg is always going to be Q squared, okay? And once again, the reason for that is because that is the only thing that I can physically see in that population. Okay, I can see the recessive phenotype, and I know that those individuals have two little letters as their genotype. So as we go through these problems, we're pretty much going to be doing the same thing over and over and over again, okay? Now, you're going to want to have a calculator handy. So if you don't have a calculator, go ahead and grab one. I'm just going to use my phone. I also have the answer key on my phone, so I'm going to be referencing that because I'm not going to take the time to work out all of the math, but I do want to show you how to do these problems. Now, you don't have any homework over Hardy-Weinberg. You've got 8 different problems on this paper here. I'm going to do one of them. I'm going to do an example on this activity here. And then Miss Petty's going to give you the answers so that you can check your work. But you don't have an official assigned homework. What you need to do is you need to do as many problems as you need to until you understand what you're doing. Because you will see Hardy-Weinberg on your quiz. Okay, when you take the micro and macro evolution quiz, you will see some Hardy-Weinberg problems. So you need to know how to do them. All right, so I'm going to flip over here. I was really hoping that I was going to be able to be there in person today, but this lesson fell on a Tuesday and I'm in class until 11 o'clock, so I wasn't able to make it there in person for this. Alright, so I'm going to write these equations up here again. Alright, so there's my 2 equations. And I want to show you how we can go about completing these. Okay, so we're going to take a look at problem number 1 on your little practice sheet here. And we're going to walk you through how to do each one. Alright, so it says you have sampled a population in which you know that the percentage of homozygous recessive genotype is 36%. So this is all we need to figure out all variables, okay? Now, one important aspect of Hardy-Weinberg is that you answer the question that they ask. So we have A through E here, okay? And so we have multiple things that we have to answer. Sometimes there may just be asking for one variable. But regardless of what they're asking for, you're going to have to go through the same general flow, okay? we're going to solve for each individual variable in these equations, and then you just have to be able to answer the question appropriately, okay? So they told us that our homozygous recessive genotype is little a, and that in the population, 36% have that genotype, okay? So as always, like I mentioned before, we are always starting with Q squared, okay? So they told us that it's 36%. Remember that our frequencies are equaling 1, so we do need to convert that to a decimal. So the value for Q squared is going to be 0.36, okay? Hope that makes sense to everybody. Once again, this is always going to be our starting point because this is what we can physically see and physically count in a population. All right, so now we have to figure out where can we go next. Okay, so we're always going to start with Q squared. The frequency there is 0.36. And if you look on letter A, that's the question that it's asking. Okay, so the first question is the frequency of the little a genotype. All right, so that's going to be 0.36. So Q squared equals 0.36. You do need to know what those variables represent, okay? When you have the problems, you'll be given the equations, but no one's going to tell you what is what. Like P is the dominant allele, Q is the recessive allele. You're going to have to know those things. So you'll be given the equations, but you have to know what they represent, okay? So Q squared is my homozygous recessive genotype. So the next thing I can do, okay, I wish I was there for you to kind of give me the answers back to these questions. But if I know Q squared, there's really only one variable that I can identify next, okay? I can't determine P squared and I can't determine 2PQ because those would have to be added together. But what I can do is if I know that Q squared is 0.36, my next step would be to find Q, okay? So Q squared is 0.36, so how do I find Q? I'm going to take the square root of Q squared. Alright, so all I do is I take the square root, and so Q is going to be 0.6. I would definitely use your calculator for this because sometimes doing the square root of decimals can be a little tricky. This one's fairly simple, but I would definitely encourage you to use your calculator just to kind of double check yourself. Alright, so now I've gone from Q squared to Q, and my next step would be to find P, because I know that P plus Q equals 1. So from Q, I go to P. Alright, and the way I find P is I say, okay, if these two are equal to 1, then I just need to do some subtracting. So 1 minus Q is going to give me P. So P is going to be equal to 0.4. So there's one of my answers. Alright, so far we have solved for P, Q, and Q squared. Okay? So now from P, I can now complete my all of my variables. Alright, so from P, I can find P squared by squaring that. Okay? So 0.4 squared, which is going to equal 0.16. And then I can also solve for 2PQ, okay? And so in order to solve for 2PQ, I'm actually going to prop this up for a second. So I take 2 times P, okay, which is 0.4, times Q, which is 0.6. And so 2PQ is going to be equal to 0.48, okay? So there's going to be one of my variables. Alright, so that's going to be your basic flow of information for every Hardy-Weinberg problem that you do, okay? You start with Q squared, because that's going to be the information given in your problem. If they don't come out and say it's this percent or this frequency, you may have to calculate it. So this is always going to be the frequency of your recessive phenotype, okay? From there, we can take the square root to find Q. From there, we can subtract from 1 to find P. We can square it to find P squared. And then we can multiply 2pq to find those heterozygotes. Okay, so technically we've done all of the math that we need to do for this particular problem. Okay, now we just need to go back and answer the questions. All right, so the very first one, A, said the frequency of the little a genotype. We need to know that that's q squared. So this is the answer to A. Okay. Now, B says the frequency of the little a allele. Well, the little a allele is going to be Q. So this right here is my answer to B. All right. C says the frequency of the capital A allele. So capital A is represented by P. So this right here is going to be C. The next question, D, says the frequencies of the genotypes big A, and big A, little a. So big A is P squared, and big A, little a is represented by 2pq. So both of these values are going to be the answer for D. Okay, so this is big A, that is big A, little a. And then the last question says the frequencies of the two possible phenotypes if A is completely dominant over little a, okay? So essentially this is asking for phenotypes, all right? So I want you to remember that q squared, this is always going to be my recessive genotype, okay, little a, but this is also always going to be my phenotype, because the only way that I can be recessive is if I have two little letters. So for letter E, for my recessive genotype, or my recessive phenotype, it's going to be 0.36, okay? Now, to find the dominant, there's two different ways that you can go about doing that, okay? There's two ways that you can find the dominant phenotype. Now, we're looking at this equation here, because this is the equation for genotypes and phenotypes. So I'm looking at p squared plus 2pq plus q squared. So I already know that this right here is 0.36. So if these are my recessives, that means both of these are going to be dominant, okay? So one way that I could find the dominant phenotype frequency is I could just simply subtract 1 minus 0.36, and that is going to give me 0.64, okay? So that's one way to find the dominant, is just subtract 1 minus q squared, because we're talking phenotype. What do they look like? Now, the other way to find it is I could add these two together, okay? Because p squared is going to demonstrate the dominant, 2pq is going to demonstrate the dominant. So I could add those together. And so if I add 0.16 and 0.48, I'm also going to come up with the 0.64, okay? So we have technically just solved for all of our questions, okay? Now, I want to just point out a couple of things about these practice problems. All of the questions are going to follow this same flow, okay? You're always going to go q squared to q, q to p, and then p to p squared and 2pq, okay? That same basic flow. But they may present the information in a little bit different ways, okay? So I want you to take a look at problem number 2. They give you all this background about sickle cell anemia, okay? They tell you about homozygous individuals and heterozygous individuals and homozygous recessive individuals. And so if you jump down to like the last sentence, it says if 9% of an African population is born with sickle cell anemia, which is little s, what percentage of the population will be more resistant because they are heterozygous, okay? So once again, we're starting with this. We're starting with q squared. They told us 9% of the population. We do need to convert that to a decimal, okay? And that will be our q squared. Now, in this case, there's only one variable that you have to solve for, okay? Because they're only asking for heterozygous individuals. And heterozygous individuals are 2pq. So the only answer is what is the frequency of 2pq, okay? But we have to go through this pattern, okay? You're going to have to start with q squared, then you're going to have to find q, then you'll have to find p, and then you can find 2PQ. So the only one that they're asking for is this one, but you're still gonna have to go through that same flow of information, okay? All right, if you flip it over, I want you to take a look at number 5, because number 5 is one that has a little bit of an extra step to it, and it's got a couple of different questions. We're still doing the same process, we're still following the same flow. But if you flip over to number 5, and I have no idea what it's talking about with red-sided and tan-sided, it's just something that's made up. But we have 396 red, and we have 557 tan, okay? So I'm just gonna get you started on this one. Because this one you have to do a little math before you get Q squared. They didn't just come out and tell us this is the percentage of recessive individuals. What they told us was that we have 396 red individuals, and we have 557 tan individuals. It says assume that red is totally recessive. Okay, so this is going to be my recessive trait. So from this, we have to calculate the allele frequencies, which are P and Q. It asks us to do all of the genotype frequencies, which is P squared, 2PQ, and Q squared. The number of heterozygous individuals that you would predict. So in this case, we're having to apply a frequency to a total. And then you're going to have to do the phenotypes, like we did on the first problem. How many recessive, how many dominant phenotype. And then it's asking you to kind of take this information further and apply it to a new total, okay? So I just kind of want to go over a few things on this particular problem. So notice they didn't tell us what my percentage of recessive individuals was. So they didn't automatically come out and tell us Q squared. So you may have to do a little extra math, okay? So hopefully we know that to find the frequency, it's going to be part over whole, okay? So what we need to know is how many recessive individuals, what is the frequency of the recessive individuals? So the first thing you're going to have to do is you're going to have to find a total here, okay? All right, so unless I'm totally mistaken, that should be 953, okay? So to get my Q squared, I have to know what is the percentage of recessive, or what is the frequency of recessive out of that population. So they told us that red was recessive. So I need to take 396, divide it by 953, and that is going to give me my Q squared. All right, can't do that math in my head, so I'm going to take a second. All right, now this is where you're going to want to round. Okay, so I got 0.41552. So I typically round to the hundredths place unless I have to carry it out further. So my Q squared for this is going to be 0.42. Okay, I am going to round. If you round differently than your neighbor, you're not going to come up with the exact same numbers. So once again, always round to the hundredths place unless, like, there's a problem where you have to carry it out past the hundredths place, okay? So this is going to be my Q squared. At this point, I'm going to follow the same things that I've done before, okay? Q squared to Q, Q to P, then I can do P squared and 2PQ, okay? So if you're looking at the questions on problem number 5, A is asking for P and Q because those are my allele frequencies. B is asking for the genotypes, so P squared, 2PQ, Q squared. D is asking for the phenotypes. So remember, if we know Q squared, we also know the recessive phenotype. And then for the dominant, you either add them together, the P squared and the 2PQ, or you just subtract this from 1. So we've already learned how to answer questions like A, B, and D, okay? Now, for C, you're going to have to do a little more math once again. It says, what is the number of heterozygous individuals that you would predict in this population? So this right here is my total population, okay? They want to know how many heterozygous people are in that population. So what I'm going to have to do is I have to find my 2PQ frequency, because that's my heterozygotes. So I would just multiply whatever that frequency was times my total, and that will give me about how many heterozygous individuals. So we just apply the frequency to the total, okay? And that's really all you're doing there. Because it's not asking for a frequency, it's asking for how many individuals. So you take the frequency that you calculated and you apply it to the total population. And then if you take a look at E, it says the breeding year, there's 1,245. So it's saying if this population increased to 1,245, assuming that equilibrium was maintained, which means all of your frequencies are staying the same, it asks how many would you expect to be red and how many would you expect to be tan. So once again, on that particular problem, on E, you're going to take your new total and you're going to have to multiply it by those frequencies. So how many would be red and how many would be tan, and that's where you're going to use the values from D, okay? Okay, because it was on D where you calculated how many you're going to be, what is the frequency of recessive phenotype, what is the frequency of the dominant phenotype. So once again, you just have to apply frequency to a total, and that will give you the answers that you need, okay? Now, I really hate that I'm not there to clarify on some of this and to be there while you're practicing though. So you need to use the rest of your class time to do the practice. You need to jot down the answers that Miss Petty's going to put on the board, and you need to make sure that you understand how to calculate all of these frequencies, okay? So just practice, practice, practice until you feel confident, okay? Make sure you know what you're doing, and then you will see some questions on the quiz, okay? When it comes to the test, just looking ahead, you will not have to do Hardy-Weinberg problems on the test, but you could be asked questions about Hardy-Weinberg, like the variables. You could be asked questions about like the conditions required to maintain genetic equilibrium, but you will not be expected to use a calculator and do problems on the actual test. This is going to be quiz only, okay? So at this point, I've covered, I think, everything you need to know. You can always go back and reference this video, or I'm sure you can find other videos on how to calculate Hardy-Weinberg. But just do the practice problems, check yourself, make sure you know what you're doing, and then just be ready for the quiz when it's coming up next week. I hope you guys have a great day. If you have any questions or concerns, just email me, and I will hopefully see you soon.